Hello. Hello, everyone. We were going to be starting with our next session for holographic displays, and it's going to be presented by none other than Mike, and he's from Swave Photonics, sorry. And I hope you have a great time. Over to you, thank you.
Thank you so much, and welcome everyone. It's a pleasure and honor to present to you today. And what we're going to be talking about is unlocking true holography, really enabling this AI plus AR computing era. And just as personal computing evolved into mobile computing, we're at the beginning of a whole new age of AI plus AR computing, where we're going to have a wide variety of ways we're going to interact with the real and virtual worlds. Ranging from smart glasses, heads-up displays, volumetric displays, holographic walls even. But it's easier said than done. And when we think about, AR plus AI, smart glasses, existing technologies, they end up being bulky, geeky, power-hungry, difficult to manufacture, claustrophobic. And they're definitely not spatial and not adapted for human vision. So, what do we really want? Well, we have a good idea, based upon the success of the Ray-Ban Meta glasses. We want glasses that kind of look like what we already wear. Fashionable, lightweight, thin frames. Prescription lenses are curved. And 60% of the world's population wears prescription lenses. And we want to keep those thin so the glasses can be light. And they need to be human vision friendly. Millions of years of evolution, have us, trained to expect things behave in a certain way, in a spatial way. And we want, binocular augmented reality. We want to be able to have dynamic depth. And we want to solve, this issue of vergence accommodation. And that's that feeling of nausea, if you've ever, worn a pair of, VR goggles or AR glasses, and after, 20 or so minutes, you start to feel, nauseous or seasick. That's what's happening. Your brain's telling you something's not right. So, what's the solution? Well, it turns out, it goes back almost 75 years. 1947, the transistor was invented. 1947, the very first papers by Alan Turing on machine learning. And 1947, the invention of the hologram. And all of these technologies are coming together now to really enable this AI at the edge, spatial computing. But what's so special about holography? Well, we've seen it in the movies for almost 50 plus years, but it's only existed as a photographic process or fancy CGI in Star Wars or Marvel movies. But it is the ultimate in 3D visualization, as we're replacing optics with pure compute and creating what really is a light field that essentially looks like the reality. And it behaves the way the human vision system expects. So if this was invented 75 years ago and we've seen it in the movies, why hasn't it become a reality yet? Well, it's easier said than done. And this chart tells us why. So on the x-axis here, I have pixel pitch. That's the distance between pixels, and the y-axis is field of view. Basically, how far can I steer a beam of light? And it's a very nonlinear relationship. And not surprising, where you really want to be is below the wavelength of light. Blue light's 450 nanometers, so you really want to be in this 250, 300 nanometer regime. Well, existing technologies, DLP, LCOS, micro-LED, state-of-the-art's 2 micron, an order of magnitude large. Not going to be practical for holography. And so what you really need to do is reinvent the pixel. Well, in fact, Swave, a spin-out from IMEC, has exactly done that, where we've invented a brand new display technology using phase change material as a pixel. And here you see a microphotograph of one of our arrays with this phase change material on top of standard CMOS. Bulk CMOS, nothing unusual about that, but we're turning it into a pixel in a display and really leveraging the low cost aspects of CMOS semiconductor foundries. And this is the world's first true holographic color display with sub 300 nanometer, half lambda pixels. We call this holographic extended reality. And it's a photonics breakthrough, but with CMOS economics. And let me tell you, how this works. And first, what is this phase change material? Well, it's a category of materials when they're gently heated, they change from one phase, crystalline, to another phase, amorphous. And this changes their optical properties. And we use that, and especially the refractive index, we use that to create an interference pattern for the hologram. It turns out we've all used this before because this is exactly what made rewritable DVDs rewritable, and in fact is commonly used as an embedded memory in semiconductors. So this is very fab-friendly materials. Just to show you how dramatically different the HXR pixel is, here it's shown to scale to LCOS and DLP, 450 times smaller than a DLP pixel. But the most important part is the relationship to the wavelength of light. This is the only pixel that's small enough to truly steer light. And blue light, we can steer it up to 120 degrees. And so this gives us the beam steering capability that's going to make holography both practical and effective. So let's talk about how this works. So here we have a pair of glasses, and this would be our HXR light engine. And we're illuminating it with just laser light, low cost RGB all at once. And by modulating the pixels, changing them from one phase to another, we create an interference pattern that basically gets reflected off a holographic optical element, a photopolymer that's right on the glasses. And that diffraction pattern creates an image that gets imaged on your eye, and we can put that anywhere in depth. So wherever we want to put the image, because this is a computed image, we can put it at arm's length. We can put it where it belongs. And this gives us a whole new aspect with respect to how do you augment reality and really behave the way we expect the world to behave. And this is also very important from an eye comfort standpoint. If everything's at a fixed 1.5 meter or 2 meter, the eye strain and eye fatigue becomes an issue. And so we really want to be able to not only behave the way the world works, but behave the way that the human vision system and the most comfortable way the eye wants to see things. That's what we can do. So we've already prototyped our first device. We call it Onyx, and the technical name is a spatial light modulator. We've put 250 million of these pixels in a die so small we can put it, embed it in a pair of frames just like this. And this is built on a standard CMOS foundry process. So what UMC in Taiwan builds this on 12-inch wafers. This is as many pixels as the Sphere in Las Vegas on a tiny die. Ooh. So with this capability, we're going to be able to go ahead and have fashionable, lightweight, comfortable, truly usable AI plus AR glasses. With all the specifications that we've been hoping for, lightweight, less than 50 grams, all-day battery life, binocular, 3D without vergence accommodation, and this ability to put multiple planes of projection, something we call dynamic depth. And because it's a computed display, we can be compatible with the user's prescription just by putting in the prescription. And so this makes the provisioning and the mass customization quite easy, and something that is compatible with how people buy glasses today. Compatible with curved lenses, and because we're using a combination of basically a simple mirror and a holographic optical element, we don't need a waveguide in terms of our overall solution, which increases efficiency and decreases weight and cost. And from some of the very first times I've experienced, we've dramatically improved capabilities while dramatically decreasing the cost. So up till now, we've viewed the world, through the lens of a smartphone camera. Well, what we're going to be able to do now is be able to visualize and interact at arm's length or at a distance. These are examples of exactly the type of holograms we're generating today. But it isn't just, being able to go ahead and, look at things. We'll be able to aid in navigation and put directions, again, at arm's length or where they belong, telling you where to turn at the place where you have to turn. Digital twin, collaboration, productivity, all get enhanced with this capability. But it isn't just near-eye applications like AI plus AR smart glasses. We're already working on adding projection mapping to physical AI, robots, and be able to have illuminated graphics that conform to any environment, as well as heads-up displays for automotive. something that today's automotive makers are incapable of, having something that is on the dashboard, but also down the road, dynamically. And so what we've described is really a whole new category of tunable photonics, where we're using these phase change materials to create ways of interacting with light and matter and all sorts of different structures. And while we've focused on holograms, it turns out across the whole spectrum, we can use these technologies for a wide variety of applications beyond the exciting opportunities we have with holography for AR plus AI. And so, to recap, we're at the beginning of a whole new era of AI plus AR computing. This is a convergence of almost 3/4 of a century of semiconductor AI and holographic innovation. And holography is really key and really essential for visual comfort, for fashionable all-day wear glasses. We're going to enable effectively superpowers, and superpowers that you'll want to use and want to wear because the glasses are so comfortable, they're no different than what you have already. And this is the beginning of a whole new era of silicon photonics breakthroughs, but with semiconductor economics. And HXR is that breakthrough. And so with that, I want to thank you so much for your time and attention, and happy to take any questions you might have.
Hello, Pejman Sek from Strathclyde University. Very cool stuff. So do you have prototypes, or is this meant to be sort of in collaboration with Meta Ray-Ban, or what's the sort of embodiment of this technology?
Great question, and thank you for that. We have prototypes, we have samples, and are already sampling our key customers, which we can't disclose at this time, but you can well imagine, given that everyone's been waiting for holography, it really is, everyone ranging from glass makers to consumer electronics makers to mobile phone companies, and also this technology is scalable. We talked a lot about and emphasized, near-eye applications like glasses. But as I showed, this is going to be scalable to other formats, including, windshields and eventually, larger displays. And so the short answer is we're engaging with customers, and over the next year, you'll start to see more and more demos and at CES, Photonics West, and even Mobile World Congress.
Okay, so it's not something that I can see now, I can try.
Not right now.
Okay, thank you.
Unless you work at one of our customers, which we're happy to arrange that.
Hi. You were talking about the pixel size of 0.5 micron, right? So, one of the problems of real-time holography is the bandwidth. Like, you need to control a lot of information in real time. So I was quickly calculating, like, in 1 centimeter, you will have 20,000 pixels linearly, and in 2 dimensions would be 400 millions. So again, you come to the problem of how to drive in real time 400 million pixels for a small field of view. How do you solve this problem?
Exactly. So fantastic question. And if you think about it, take all the information on your smartwatch. That's a bitmap. And so that level of information is quite easy to transmit with Bluetooth because we do that already. And what we've actually partnered or really have a companion to our display chip, a little compute chip that translates anything from a bitmap all the way to more elaborate or perhaps exotic information from 3D Blender, Unity content, but turns it into the holographic format that we need to program our pixels. And so what we've done is we've simplified one of the real challenges of holography is exactly that. How do you get lots of information to where you need it? What we've done is we've localized it here, and so that that problem of high bandwidth, which is not only power consuming, but takes up a lot of communication. We've changed that and turned it upside down and really removed it from an issue, because for the first and really perhaps mainstream AI plus AR glasses, what you want is all the functionality here, but here. And do it in a way that adds value and puts it in the proper projection plane. And by doing it in this way and keeping the compute local, we've eliminated that as a problem. And still low power enough that we can get all-day battery life, from a battery embedded in a pair of glasses.
Thank you.
Yeah, thank you. Question: what's the update rate? You're talking about phase change material, so how fast can you change this?
Yeah, so another great question, and what you forgot to mention and really emphasize, and you may have caught on, this is a bistable, like e-ink process. But unlike e-ink, very fast, transition time. It's about 200 nanoseconds in one change, going from amorphous to crystalline, about 300 nanoseconds, going the other direction. And then once we have an image, we can actually turn the display off. And so this becomes a huge power savings. And so very fast, refresh rate and the ability to retain state, so that, just like, navigation, you're not updating that, or an emissive display, needing it to refresh to get a persistent image. So we get the best of both worlds, very fast refresh and the bistability that reduces our power consumption dramatically.
Okay, thank you.
Hello, excuse me, can you clarify the brightness of the virtual image and efficiency of this device? Yeah, thank you.
Fantastic question. And so for a normal day wear, you're respecting, in excess of 2,000, nits. But the cool part about holography is we can beam steer and put, information, basically light, where we want it. And so we can burst up, in terms of what we need, with respect to ambient conditions. And so that's, one, nice benefit, again, of a computational display and a beam steering display. And then at a systems level, it turns out, because we're eliminating, elements of traditional systems that aren't very efficient, we end up at a systems level much higher efficiency, anywhere between 3 and 5x, better than existing solutions, just because, we're approaching this problem in an entirely different way, and one that's very well suited, especially for AI plus AR glasses.
Any other questions? I think we are before time in that case. Our next session is going to start at 5.
Thank you very much, and I really enjoyed presenting.
Yeah, thank you.